Good morning, everybody. This is Mukherjee, working as Associate Professor in St. Peter's Engineering College, Physics Department. So today we are going to discuss about the davission and germer experiment, which successfully gave the demonstration of the de Broglie wavelength as well as to a much approximate accurate level the wavelength of the electron. Because de Broglie has said that everything in the universe is a matter wave now. A matter can behave like a wave can also behave like a matter. So we know that electron, of course, it's a matter, it's a particle being like a wave. So de Broglie's, according to de Broglie's theory, electron should also behave like a wave. And it was J.P. Thomson who first experimentally demonstrated that electron behaves like a wave, and who is the son of J.J. Thomson. So J.J. Thomson, who is nothing but who said that the electron, or who gave the particle properties of wave, especially the specific charge of electron and other things. His son also become famous by proving that electron also behaves like a wave. So this is what the basic conditions or basic representations of this thing. But we have a problem in the J.P. Thomson experiment. It wasn't good enough to calibrate or to give the accurate value of the electron wave. Therefore, we required another experiment, and that is given by davission and germer experiment. So let us see how this davission and germer experiment is demonstrated. So this is exactly the arrangement of the davission germer experiment is. What is it we have? We have a chamber. In that chamber we have a cathode filament, and this cathode filament is connected to high tension. And this cathode filament is connected to high tension. What is going to happen? The cathode is going to release the cathode rays, of course the electrons. And these electrons are going to come and fall on the nickel. We call it as a nickel crystal. A nickel crystal is mounted on a toggle, something like this. This is a toggle and this is nickel. So this nickel metal is mounted on this, so that we can rotate this toggle. We can rotate the toggle in this way. So when it is rotated, what is happening? Even the nickel will also move in this direction. So depending upon this direction, what is happening? The electrons will be coming and hitting the nickel, and after that they will be reflected, and this reflected rays will be falling on the, what is that? We have a Faraday cylinder which is mounted on a circular scale, and this Faraday cylinder is connected to a galvanometer, and then which is grounded. So this galvanometer is going to give us the current, using which we are going to calculate the voltage, and from that voltage we are going to determine, or we are going to find out whether these electrons which are released from the cathode rays falling on the nickel, reflected and received or sensed by this Faraday cylinder, we call it as a Faraday cylinder, mounted on a circular scale. A Faraday cylinder is mounted on a circular scale at different angles and different lengths, and which is connected to a galvanometer. From that we try to calculate the voltage, and we try to find out whether this lambda equals to the equation which is given by 12.26 by root V. Is it going to give the wavelength of an electron? Here, before going to that, we mounted a Faraday cylinder. Now what is the use of a Faraday cylinder? Why do we require a Faraday cylinder? We require a Faraday cylinder. Cylinder. What is the cylinder actually? A cylinder is nothing but, it's an arrangement. It's an arrangement. Why do we call it a Faraday? Let us discuss about this arrangement, and then we will go into the detail of this part. What is the specialty of this cylinder? The cylinder is an insulated one. You are going to have a box followed by insulation followed by another box, and the inner box is connected to the galvanometer. So this is what it is. This is what it is. What is the case? You have a metallic box, and you have another metallic box. A smaller metallic box is inside of a bigger metallic box. Both of them are insulated. In the sense, both of them are separated. There is actually no space. Let's call it as a vacuum. Let us call it as vacuum. So what is there? There is a vacuum between these two boxes. So when there is a vacuum, what does the vacuum does? Vacuum doesn't allow any particle Vacuum doesn't allow any radiation except light. A vacuum only allows the light. It doesn't allow any other rays. Why? Because vacuum, how other rays will be moving? Other rays require a medium. How exactly the waves will be moving? We know that you take a water, put a stone in the water. What happens? The ripples are created. And how these ripples are created? The stone is going down. When the stone is going down, what is happening? It is creating a disturbance, and that disturbance is moving in the water. Why? Because there are water particles which are carrying the disturbance all around the water. So we require water there to see the disturbance. Similarly, we require particles, and that particles will carry the energy. Particles will be actually carrying the energy from one point to the another part. So what is the way? It is a transmission of energy from the particles. But a light, no. Light, it doesn't require any particles, because light itself is something which is very special enough. Even it moves in the vacuum because it doesn't require any particles. It moves in the vacuum, and that is the reason why we in the morning just get up, we see the sun. The sun is actually older sun. Older sun in the sense he is 8 minutes, 8.5 minutes older to the actual what you are seeing. Why? Because it takes 8.5 minutes for the sun rays to move from sun to earth, and between sun to earth what is there? Space. And what is the space? Vacuum. What is space? It has vacuum because it doesn't have any media, it doesn't have any nitrogen, it doesn't have any oxygen, it doesn't have any phosphorus, it doesn't have any calcium, it's only vacuum. But the light is still moving, it is taking 8.5 minutes. So light is something which actually moves in a vacuum. So here what is that we are taking? We are taking double insulated rods. In the sense we have taken a metallic box surrounded by a vacuum and placed in another metallic box. Right. But why do we require this? Why do we require this? Because we need to see whether the current or the voltage that is measured here is because of the electron wave, or is it because of the electrons? Because even an electron, when you connect in a circuit, when you circuit a galvanometer, the galvanometer will be displaying the changes because the electrons are moving where the electricity is flowing. So galvanometer responds to the electricity, right? So in order to avoid that, we don't want electrons, we only want electron rays. He made this Faraday cylinder. Actually, why do we call it as a Faraday cylinder? Now, what is the Faraday? Faraday is nothing but a unit of capacitance. What is the capacitor? Capacitor is nothing but two metallic plates supported by some space. That's what a case is. You're going to have the capacitor here. And what is the capacitor? The capacitor is two metal plates which is connected to some potential. And what is it you're going to have? You're going to have plus charges here, you're going to have a minus charges here, and the electric lines will be flowing here. So what is happening? The electrons will be coming here and the electric lines will be flowing from this part to this part, and this electric lines will be ending here and they will be kicking the electrons, and therefore electrons will be moving here. Electrons will be coming here, and now there is no further medium to carry the electrons, therefore it releases the electromagnetic lines or electric lines. These electric lines from this corner to this corner, they go and hits this capacitor or the other plate of the capacitor. There once again electrons are ready, they take this electric lines, and according to the lines, once again they will be taking the motion and they will be moving in this direction. This is exactly a Faraday cylinder, or a Farad. We call it as a Farad. It is a capacitor. He actually designed this capacitor. So the unit is of a capacitor is named after him. So we call it as the Farad as a unit of capacitor. So something similar to this, we have taken this. So here now what is happening? Let us see what is happening. What is happening? The electrons are coming and they are narrowed down. Here we have a pencil type of opening. They are narrowed down, and these narrowed down electrons are falling on the nickel crystal on a toggle. So this toggle will be rotated here in this way. So the nickel will also move in the direction. When this is moving, the nickel is also moving in the different directions in this way. The electrons will be coming and hitting this. They will be reflected in different directions, and they will be coming and falling on the Faraday cylinder. Now here the catch. The catch is here now. What is happening? All the electrons will be coming in here, falling on this nickel. And this is mounted on a cylindrical scale, so we will be moving here in that. We will be moving this circular scale in different angles. So now what actually happens? Let us see what happens. Electrons, they are coming and hitting this metallic plate. They will be coming and hitting. Let us assume that electrons are coming and hitting the metallic plate. Of course, metal. What is the metal? It's a conductor. So it sends all the electrons to all around the corners. After that, the electrons cannot move into the space. The electrons cannot move into the space because it's a vacuum, and electrons can never move into vacuum because electrons require a medium. Even an insulator, even though it doesn't conduct, but still it is a medium. It is a medium, at least it allows the electric lines. But here what is there? You have a vacuum. So you have a vacuum now. So now what happens? The electric lines will not move in a vacuum. That is assumed. Actually it moves, but here what is happening? The electrons are coming now. The electrons are coming and they are hitting this now. When the electrons are coming and hitting this, what is happening? All the electrons are getting deposited, but they can't move further down. So what is happening? The deposit of electrons is happening on this. So electrons are getting mounted and mounted and mounted and mounted and mounted. So a huge amount of electrons are mounted on this. So therefore what happens? There will be a collision among these electrons. A huge amount of collision happens, and therefore what happens? A high amount of energy is produced, and one of the electron takes that high energy, it becomes a wave now. When it becomes a wave, what happens? Wave will transfer to this. So electrons will be moving from this edge to this edge. It comes and it settles on this. Once again, its velocity is reduced, and therefore it becomes an electron, and that electron results in the galvanometer. So what is happening? The electrons are coming and mounting on this top surface. They are getting piled up. They are getting deposited. They are getting deposited. What is happening? A pile of a huge amount of electrons are produced. When this huge amount of electrons are produced on this, a heavy collision is happening among themselves. When a heavy collision happens, what happens? High amount of energy is produced. So one of the electrons picks up that high energy, and it becomes a wave now. So this is the condition. That is what De Broglie said. We require to have a separate condition. When condition is achieved, then electron also behaves like a wave, and now the electron is behaving like a wave now. So electron becomes a wave, and this wave can move through the vacuum. It is moving and it is hitting this. Once again, it loses its properties. It will be once again electron gains its particle properties, and therefore it is measured to a galvanometer. In that way, what is that we will be doing? We will be making this Faraday cylinder to move on the circular scale in different angles. We will be making this to move on a circular, different kinds of circular scales and all these things. So this is what it happens generally. So now we will be taking these readings. We will be taking the readings and we will be trying to plot a graph. When we try to plot a graph, we are going to get the graph in this way. These are the reflections, and so on. These are the reflections, and this is the intensity of the radiation. So we are going to plot a graph. When we plot a graph, we are going to get the graph representation in this way, right? So what is the equation? Lambda equals to 12.26 by square root of v. So here we are going to use the Bragg's law. They have used this Bragg's law. Now what is Bragg's law? First of all, what is Bragg's law? Bragg's law, it says that 2d sin theta equals to n lambda. This is what a Bragg's law equation is, or it can also be written as a sin theta equals to n lambda, where v equals to 2d. What is the Bragg's law? You know, we have the matter is classified into solids, liquids, and gases. You know that. And solids are further classified into two categories: crystalline and amorphous. What is the crystalline? Crystalline is something which has a uniform properties. I don't say uniform, but regular. Crystalline has a regular properties. You take a big crystal, remove a small crystal from that. This crystal will have all the properties what a big crystal will have, or this big crystal will have all the properties what a smaller crystal will have. But in an amorphous case, it is not that. The case is not that, and they don't acquire, or they are not available in such a beautiful conditions. To understand, to find out why is this happening, because the atoms are arranged in a very regular way, not uniform way. They are arranged in a regular way, and this regularity. How these materials are classified? They are classified in several places, like triclinic, monoclinic, orthorhombic, tetragonal, hexagonal, trigonal, simple. There are 7 different types, and these 7 are further classified in 14 classes. We have this classification of these crystalline structures, but this is only done depending upon what? The distance between the atoms along x-axis, distance between the atoms along y-axis, distance between the atoms along z-axis, and the angles at which these atoms are aligned along x-axis, y-axis, and z-axis. So how these crystalline properties are? They are arranged regular way. What do you mean by regular way? The distance between the atoms are very specific, and it is same, and the angle at which these atoms are arranged are also the same in a bigger crystal and a smaller crystal. But how do you know these properties? We will be using this Bragg's law. So this Bragg's law will be using this optical properties. Using these optical properties, it actually calculates the interatomic distances between the planes or between the particles in a crystal. So now he has taken this particle property. But this particle property is now used to calculate the wave property of this electron. So here, what is the we are going to take? We are going to take 2d sin theta equals to n lambda. So now we have taken the nickel crystal. A nickel crystal, the interatomic distance. The interatomic distance is approximately d is given by approximately is 2.15 into 10 power minus 10 meters. It is taken approximately 2.15 into 10 power minus 10. Sorry, 0.215. Sorry. It is taken as 0.215 into 10 power minus 10 meters. And therefore, we are going to take over. And what does this n stand for? Either it can be first, second, third. We call it as levels now. Orders. We call it as orders or first level, first order, second level or second order. So n we want to take first order. So we know this value and theta. Here we want to take theta is nothing but 90 minus 25. Why 90 minus 25? We are taking the complementary angle. So what is the we want to substitute this value? What are the values we want to substitute? We want to substitute 2d sin theta equals to 1 into lambda. So 2 into 0.215 into 10 power minus 1 into sin of 90 minus 25 equals to lambda. And finally, what is the lambda we are going to get? We are going to get a lambda of approximately 1.648 Armstrongs. This is the value we are going to get using this. Because we know the interatomic distance. When we know the interatomic distance, we can calculate the wavelength of the radiation that is falling on this interatomic distance crystals. So we are going to get the wavelength of this. This is the wavelength. Whose wavelength is this? These waves. And this is calculated experimentally. Different angles, and depending upon these different angles, we are getting the wavelength. And this wavelength is given by lambda equals to 1.648 Armstrong units. So this is what we know this. This is what generally the case is. This is what wavelength is. Now let us see theoretical value. What is the theoretical value we have? Lambda equals to 12.26 by root v. So what is the we want to do? We want to substitute 12.26. The voltage that we applied here is approximately 54, which is 1.668. See the difference. Here it is 1.648, and here it is, what is the case? 1.68. So what is the calculated value? The experimental value is 1.648, and what is the theoretical calculated? 1.668, and both are almost. There is only a change at the second decimal of the 10 power minus 10 meters, which proves, which gives an accuracy, which gives an accurate value of the electron wave like a wave. How did this started? The electron rays, like a particles, they were moving, they were hitting the nickel target, and this nickel target was toggled, it was moving in this direction. So this nickel was attached to this. When the nickel was attached to this, what is happening? We were moving this in this way. So what is happening? The rays are coming and hitting this. They were reflected in the different angles, and this reflected rays are collected to the Faraday cylinder, which is mounted on a surface scale. And what is the Faraday cylinder? You're going to have a metal box followed by a vacuum followed by another metal box. So now the radiation will be coming and hitting the first box, and they will be deposited on this. But the piling up of the atoms will be happening. When the piling up of atoms happen, all the electrons will be piled up there. When all the electrons are piled up, what happens? A huge amount of energy, because the collisions will be happening there. Because the electrons are coming in, falling on this. Still the number of electrons are coming with energy, they will be moving and they will be coming and falling on this. So the piling up of electrons is happening and a huge amount of energy is produced. And one of the electron will takes up this huge amount of energy and it becomes a wave. That is what the de Broglie wavelength is. De Broglie wavelength says that under specific conditions, matter behaves like a wave. And this is a fantastic example where the matter is behaving like a wave. So the particle is beautifully behaving like a wave, and that is demonstrated with this experiment. Lambda equals to what? So therefore, the wave electron will be moving through the vacuum. It will be coming and falling on this. It loses its wave properties. It becomes a particle here, and this particle electron will be producing electricity, and this electricity will be measured by a galvanometer. And when we substitute the theoretical value and practical value, both are in agreement to each other. And this is a beautiful demonstration. So earlier, what was the case? The first case was G.P. Thomson experiment. And what is the case in G.P. Thomson experiment? The G.P. Thomson experiment is, he could only calculate or he could prove that the electron behaves like a wave, but the accuracy level of this electron's wavelength was not good enough. Was not good enough with the measured values. But here, the measured values and the calculated values are both in agreement to each other. So the de Broglie says that any of these waves behave like a wave. Matter behaves like a wave, wave behaves like a matter. And G.P. Thomson was the first person to prove that electron behaves like a wave. And Davisson Germer was the first person, you got correct the first person, but they were successful enough to give exactly or the accurate values of the wave length. And this is where the quantum mechanics beauty lies now. Even you and me can become a wave. How can we become a wave? Why are we not a wave? Because we have a specific mass, we have a specific density, we have a specific volume. For example, I'm 100 kgs now. When I'm 100 kgs, what does that mean? I'm occupying some volume. I'm having this 100 kgs, now I'm a particle. But I can also behave like a wave. What are the conditions? The condition is that my mass has to be reduced. If my mass is reduced, any of the cases if my mass is reduced, that's it, I'll become a wave. This can be applied to anything, this can be applied for any object, and that is the objective of this Davisson and Germer experiment is. So quantum mechanics had a deviation with respect to the classical mechanics. The classical mechanics could not explain all these properties. We are living in a modern world. You know what is a modern world? Which uses the quantum principles. We are living in a modern world. What is the modern world? Now we are into augmented reality now. We are into augmented reality, or we are into what is it we call it as artificial intelligence. We are driven by the artificial intelligence. So this is only possible only because of quantum mechanics. Thank you very much.